When tapping from the line troughs of indoor multimeter centers, the National Electrical Code, or NEC, mandates a specific calculation. This calculation is represented by the formula T equals R multiplied by I, where T represents the total ampacity required in amps, R signifies the resistance per foot in ohms per 1000 feet, and I denotes the total length of the tap conductor in feet. For a 200 amp single-phase service, the calculation unfolds as follows: T equals 200 multiplied by 0.8, resulting in 160 amps, taking into account a power factor of 0.8. The resistance, R, is specified as 2.32 ohms per 1000 feet, assuming a 3/0 THWN copper conductor. The variable I corresponds to the distance from the line trough to the meter socket. A commonly used rule of thumb for tapping from multimeter centers involves employing a tap conductor with an ampacity that is 75% of the main service ampacity. In the context of a 200 amp service, the tap conductor could be sized at 150 amps, obtained by multiplying 200 amps by 0.75. The calculation for this rule of thumb is expressed as T equals R multiplied by I, where 150 amps equals 2.32 ohms per 1000 feet multiplied by I. Solving for I yields a result of approximately 64.6 feet. Consequently, the tap conductor could extend up to 65 feet if a 150 amp conductor is utilized. It is advisable to adhere to the code-compliant calculation method outlined in the NEC, as it guarantees compliance with electrical safety standards. While the rule of thumb method serves as a helpful guideline, it is crucial to validate it with the actual calculation to ensure both safety and code compliance. Additional considerations include ensuring that the line trough possesses sufficient capacity for the additional tap conductor, opting for copper conductors with appropriate insulation suitable for indoor use, such as THWN or XHHW, providing proper support for the tap conductor and securely connecting it to the service entrance conductors, securely mounting the meter socket and the wall or panel, and installing overcurrent protection devices, or OCTs, as mandated by the NEC. In essence, when dealing with electrical installations, meticulous adherence to established codes and standards is paramount for ensuring safety and regulatory compliance. The NEC serves as a comprehensive guide, providing detailed instructions and requirements for electrical work. In the context of tapping from multimeter centers, the code mandates specific calculations to determine the appropriate conductor sizing and protection measures. The formula T equals R multiplied by I, where T represents the total ampacity required, R signifies the resistance per foot, and I denotes the total length of the tap conductor, forms the basis of these calculations. By accurately determining these parameters and applying the formula correctly, electricians can ensure that a tap conductor is adequately sized to carry the intended load without exceeding its ampacity rating. Furthermore, the code stipulates the use of appropriate insulation for conductors used in indoor environments such as THWN or XHHW. These insulation types offer the necessary protection against environmental factors and electrical hazards. Proper support for the tap conductor is also essential to prevent strain and damage, while secure connections to the service entrance conductors guarantee reliable electrical continuity. Overcurrent protection devices, such as circuit breakers or fuses, are critical components of the electrical system, safeguarding against overloads and short circuits. The NEC mandates the installation of OCTs at strategic locations to protect both equipment and personnel. In addition to the code-compliant calculations, a rule of thumb is often employed as a quick estimation tool. This rule suggests using a tap conductor with an ampacity that is 75% of the main service ampacity. While this rule provides a convenient starting point, it is crucial to validate it with the actual calculation to ensure its accuracy and suitability for the specific application. It is important to note that electrical work can be inherently dangerous. An unqualified individual should never attempt to perform such tasks. Only licensed and experienced electricians possess the knowledge and skills necessary to safely and effectively install and maintain electrical systems. When in doubt, always consult with a qualified professional to ensure that all work is performed in accordance with applicable codes and standards. Electrical installations should always be approached with caution and respect, prioritizing safety above all else. By adhering to established codes, employing sound engineering practices, and seeking expert guidance when needed, it is possible to create safe and reliable electrical systems that serve their intended purpose without posing undue risks. In summary, compliance with the NEC is not merely a legal requirement but a fundamental aspect of electrical safety. By diligently following the code's provisions and incorporating industry best practices, electricians can contribute to the well-being of both people and property. Remember, when it comes to electrical work, there is no substitute for knowledge, skill, and unwavering commitment to safety. In the scenario presented, tapping a 200 amp single-phase 23 kilowatt service from the line trough of an indoor 600 amp 3-phase multimeter center containing 30 meters requires careful consideration of several factors to ensure code compliance and safety. Firstly, it is essential to verify that the line trough has sufficient capacity to accommodate the additional tap conductor. The trough should be sized to handle the combined load of all connected services, including the new 200 amp tap. If the existing trough is undersized, it may need to be upgraded to a larger one to prevent overloading and potential hazards. Secondly, the selection of the appropriate conductor size for the tap conductor is crucial. The NEC provides guidelines for conductor sizing based on ampacity and voltage drop. The ampacity of the conductor must be sufficient to carry the 200 amp load, while the voltage drop should be minimized to ensure proper operation of the connected equipment. Factors such as conductor material, insulation type, and ambient temperature also influence the conductor's ampacity rating. Thirdly, the tap conductor must be properly protected against overcurrents. Overcurrent protection devices, such as circuit breakers or fuses, should be installed at the point where the tap conductor originates from the line trough. The OCT should be sized to protect the conductor from overloads and short circuits. The NEC provides specific requirements for OCT sizing based on conductor ampacity. Fourthly, the tap conductor must be securely connected to the line trough and the meter socket. Proper termination techniques should be employed to ensure a reliable and low resistance connection. Loose or corroded connections can lead to overheating and potential fire hazards. Fifthly, the meter socket must be securely mounted to a suitable surface. The mounting method should be appropriate for the type of wall or panel to which the socket is being attached. The socket should be installed in a location that is readily accessible for reading and maintenance. Sixthly, all wiring and equipment must be installed in accordance with the NEC and local electrical codes. The NEC provides comprehensive guidelines for electrical installations covering topics such as wiring methods, grounding, bonding, and overcurrent protection. Local electrical codes may impose additional requirements that must be followed. In addition to these technical considerations, it is important to obtain the necessary permits and inspections from the local electrical authority before commencing any electrical work. Permits ensure that the work is performed in accordance with applicable codes and standards, while inspections verify that the installation meets the required safety standards. It is also advisable to consult with a qualified electrical engineer or contractor to ensure that the installation is properly designed and executed. Electrical work can be complex and potentially dangerous, and it is always best to seek expert guidance when in doubt. In summary, tapping a 200 amp single-phase service from a multimeter center requires careful planning, meticulous execution, and strict adherence to applicable codes and standards. By addressing all of the relevant factors and seeking expert guidance when needed, it is possible to create a safe and reliable electrical installation. Regarding the resistance value of 2.32 ohms per 1000 feet for a 3/0 THWN copper conductor, it's important to understand that this value is an approximation and can vary depending on the specific manufacturer and temperature of the conductor. The NEC provides tables in Chapter 9 that list the resistance and reactance values for various types of conductors. For accurate calculations, it is recommended to consult these tables or the manufacturer's specifications for the specific conductor being used. The power factor of 0.8 used in the calculation is a typical value for residential and commercial loads. Power factor represents the ratio of real power to apparent power in an alternating current circuit. Loads such as motors and transformers draw reactive power, which reduces the power factor. A lower power factor results in higher current draw for the same amount of real power. Utilities often charge customers with low power factors, as it puts a strain on the electrical grid. Power factor correction can be achieved by adding capacitors to the circuit, which compensate for the reactive power drawn by inductive loads. The length of the tap conductor is an important factor to consider when calculating voltage drop. Voltage drop is the decrease in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The voltage drop can be calculated using Ohm's law, where voltage drop equals current multiplied by resistance. The resistance of the conductor depends on its length, material, and cross-sectional area. The longer the conductor, the higher the resistance and the greater the voltage drop. Using larger conductors can reduce voltage drop, but this comes at a higher cost. It is important to strike a balance between conductor size and voltage drop to ensure optimal performance and efficiency. The rule of thumb of using a tap conductor with an ampacity that is 75% of the main service ampacity is a conservative approach that helps to ensure safety and prevent overloading. However, it is not always necessary to use such a large conductor. The actual ampacity required for the tap conductor depends on the load it will be serving. If the load is relatively small, a smaller conductor may be sufficient. It is important to calculate the actual load and select a conductor with an ampacity that is adequate for the load. The NEC provides guidelines for calculating load based on the type of equipment being served. It is important to note that the NEC is not a design manual. It provides minimum requirements for electrical installations. It is up to the designer to ensure that the installation is safe and meets the needs of the customer. In some cases, it may be necessary to exceed the NEC requirements to achieve a desired level of performance or reliability. For example, a designer may choose to use larger conductors than required by the NEC to reduce voltage drop or improve energy efficiency. Additional considerations for tapping a 200 amp single-phase service from a multimeter center include surge protection, grounding and bonding, and labeling. Surge protection devices, or SPDs, can protect sensitive electronic equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at other strategic locations throughout the electrical system. Grounding and bonding are essential for safety. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electrical shock. The NEC provides detailed requirements for grounding and bonding. Labeling is important for identifying circuits and equipment. All circuit breakers and disconnects should be clearly labeled to indicate the loads they serve. Equipment such as transformers and generators should also be labeled with their voltage, ampacity, and other pertinent information. Proper labeling can help to prevent mistakes and improve safety. In addition to the NEC, there may be other applicable codes and standards that must be followed. These may include local building codes, fire codes, and accessibility standards. It is important to be aware of all applicable requirements and to ensure that the electrical installation complies with them. Electrical work should always be performed by qualified professionals who are trained and experienced in electrical safety. Electrical hazards can be deadly, and it is important to take all necessary precautions to protect yourself and others. Always to energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not comfortable working on electrical equipment, it is best to hire a qualified electrician to do the work for you. Finally, remember that electrical safety is everyone's responsibility. By following the guidelines and recommendations outlined in this discussion, you can help to create a safer electrical environment for yourself and others.